Hello, in this quick video, I'm going to show you how to simulate different CPU scheduling algorithms in a C program. Basically, what I'm going to do is I'm going to write a C program so that it can simulate um, the way first come, first serve, shortest job first, shortest remaining time, and priority scheduling algorithms will schedule different processes, let's say n different processes, and give them CPU. And then at the end, I'm going to print the average turnaround time for each of these algorithms under different settings. So what we are supposed to do is to keep track of multiple fields for every process in a given simulation, like the field active, which is going to be either true or false. Active means the process is currently in the CPU, and not active means it's not. Then we have the arrival times, which is given as a uniform distribution between 0 and some value k. We have Li, which is the priority level. It's a uniformly distributed random variable from 1 to 10. Then you have Ti, a randomly chosen number, which is normally distributed with an average of D and standard deviation V that specifies the total CPU time for each process. And Ri, which is initialized to Ti, that's going to be the remaining time of each process. So you can think of a process as a combination of these fields. That's how we see a process in the simulation. Now, what we need to do is to run this pseudocode. Basically, as long as there is one process with a non-zero remaining time, we need to basically choose an active process based on the scheduling algorithm, and then give the CPU to that. By doing this, the remaining time of that process will decrease. If the remaining time becomes 0, then we are going to set the active flag of that process to 0 or false, and then we are going to calculate the turnaround time. At the very end, after all processes finish, we are going to calculate the average turnaround time, and then we are going to print it, basically. The C program that I'm going to show you that does this simulation basically needs some command line arguments. The command line arguments that we need for this program would be -n flag, which shows the number of processes, -k flag that shows basically the time arrivals, basically when each process arrives. K is going to be the maximum arrival time. So basically, if K is 1,000, that means the processes will arrive from time 0 to 1,000. And then we have two more flags, -d and -v, for receiving the standard deviation and mean of CPU times, because as I said before, the CPU times are assumed to be normally distributed. And then we have time quantum for the last scheduling algorithm, which is a priority scheduling algorithm with round robin as a tiebreaker. I'm going to show you this C program, and then I will briefly talk about how to run that program multiple times for multiple scenarios. You're asked to basically create 4 different scenarios. One is when you have 100 processes which arrive from time 0 to 1,000. The other one is a scenario where 500 processes arrive from time 0 to 10,000. This is the third scenario where n is 500 and k is 5,000. And the last scenario where n is 1,000 and k is 10,000. Under each of these scenarios, you need to set the values of d, k, and v in the following fashion. I'm sorry, d, v, and q in the following fashion. D should be a number varies from K over N all the way to 25 times K over N with a step of K over N. V is going to be set to D over 4, and then the minimum value would be 1. So, of course, D is a big enough value so that D over 4 will remain positive. And then Q should be set to D plus V. With these information that we receive from the assignment, let's get into the detail of our simulation. Let's see. So here is the code I have created. We have a few functions, helper functions for our main function. I'm going to start with the main function. We need to have 11 arguments because we need two for dash n, because we need to get the number of processes. We need 2 for a dash k. We need 2 for a dash d, the mean CPU time. We need 2 for standard deviation CPU time, dash v. We need 2 for dash q. And then the first one would be always the executable name, so a total of 11 arguments. If that's not the case, we are going to print out this error message, and then we're going to return with a fatal error. If not, then we are going to make a sense out of each argument. We are going to parse all the arguments and use A to I to convert the numbers passed by a user to actual values. And then we store them in N, K, D, V, and Q. These are all external variables defined this way. These are my simulation parameters. And then I'm going to call initialize processes. Initialize processes is a function that is going to first create a random seed for my random number generator in C programming language. The seed would be the current time, and that's basically guaranteeing that anytime that you run this, you're going to get a different sequence of random numbers. Then we go over this for loop and initialize all the values for our processes. Before I go through this and show you what this for loop does, I need to tell you what processes is. It's an array of this many processes. This many is defined in the simulation.h. If you go to simulate.h, you can see that max processes is set to 1,000 because we don't have more than 1,000 processes in all the 4 scenarios. Then you see process is a structure that has an ID. That means, a number from 0 to the number of processes minus 1. And then you have arrival time, total CPU time, remaining time active, turnaround time, and priority. All of this would be inside a structure called process. And then we have an array of processes called processes with the maximum capacity of 1,000. So this is the summary of what we have in the initialized processes. What we want to do is we're going to set the ID to I, where I is a number from 0 to n minus 1. And then basically the arrival time would be uniformly distributed between 0 and k. The total CPU time should be always a normally distributed random number, which this is basically a macro that I have defined in the simulate.h. You can check it out here. It uses a complex formula to calculate a normally distributed random number. This macro uses frand, which is basically a macro that generates a random number from 0 to 1. And frand is defined using rand, which is basically a standard C function that generates a uniformly distributed random number from 0 to rand max. Rand max is a constant defined in C libraries. Now, Why do we have a while loop? Because we want to make sure the normally distributed random number that we generate is not non-positive. Should be positive. If it's less than 1, then we are going to try again. So that's why we have this while loop. Then we are initializing the remaining time of each process to the total CPU time, because initially, the remaining time should be this, but eventually after the simulation progresses, the remaining time of all processes will become 0 at the end. But they gradually, reduce until they become 0. Then the active property or active field of each process would be 0, except those who arrive at time 0. Those would be 1. And then the turnaround time would be 0. Priority would be a number between 1 and 10. That's why we use rand mod 10. It's going to give us a number from 0 to 9 plus 1. It becomes a number from 1 to 10. The plus 1 will shift everything 1 cell to 1 unit forward. So the rand mod 10, which tops at 9, becomes from 1 to 10. Now that we have seen what initialize processes function do, let's get into the details of simulate FCFS. In this video, I only want to show you this one, but you will do simulate shortest job first, simulate shortest remaining time, and simulate priority with round robin as tiebreaker yourself. So let's get into the first come, first serve. In this function, as you see, I have it in a different C file. I have included two header files, simulate.h and q.h. Q.h is a header file that basically creates a queue using a linked list. This is my linked list node. We have a process as value of the node in the linked list and then next reference. So it's a single linked list. And then the queue would be made of a head, a tail, which are both node stars, and a size, which is an integer. We have a function called init queue, which is going to construct a new empty queue. InQueue, which adds a new process to the queue, and DQ, which removes the process from the queue. And also we have a peek function, which basically just looks at the head of the queue without removing it. So that's the difference between peek and DQ. Remember, in a peek, Q is passed by value, but in a DQ and InQueue, Q is passed by reference, because in the InQueue and DQ operation, we are going to actually change the size of the queue, so we need to pass it by reference. Then also I have a toString method for the queue, so that whenever we want to print it, we can just pass this function and print the content of the queue. That's mostly for the debugging purposes. Let me go back to the queue.c. Well, I was in simulate.c, but let me also show you what queue.c looks like. This is the init queue function. That's easy, it just initializes the fields of queue to an empty queue settings. And then you have an InQueue, which basically injects a node at the end of the linked list and increases the size by 1. DQ basically removes one node from the head. If the queue is empty, it's going to return an empty process with all -1 as features of that process, which basically means something went wrong. But if not, it's just basically removes the head and returns the DQ'd process. Peek does a similar job as DQ, but it doesn't remove the node from the queue. It just returns the head value. And then the toString method basically goes through all the nodes of the queue and prints a string in the following fashion. It basically first prints front end, followed by the open bracket, and then it puts different values, let's say P2, P1, P0, P4, P3 are currently my queue content, so it prints something like this. and then it prints NQ, or I think it prints rear end, sorry. So this way you can see the content of the queue. This is only for debugging purposes. It doesn't help you with the assignment. All right, so I was telling you the simulative CFS is a function that uses a queue. So I went through the queue and showed you that. I'm going to call that queue the ready queue. Basically, that's the queue that newly arriving processes will join. And that's the queue that we use to enforce the first come, first serve, or first in, first out order of running processes. First, we define an integer complete. It's completed, we set it to 0. That counts how many processes have terminated. And if the completed becomes n, we're going to get out of the while loop, and that would be it. We end the simulation. The first thing we're going to do is we are going to, if you want to print the ready queue, you can print that. Otherwise, forget about it. Let's just skip all of that. I don't want to print anything for now. Let's get into the body of the simulation. The first thing I want to do is I'm going to check out, by the way, I forgot to say we have an integer time that's going to represent the current time. That's t represent the current time. To start from 0. In every iteration of the while loop, we are going to go through all the processes that we have in the array of processes and see which one has arrived at time t. So if their arrival time matches t, which is the current time, we're going to make them active, and we're going to add them to the ready queue by using an enqueue function. If the ready size is 0, that means if no process is ready, we have nothing in the queue, we are simply in ++ing t, and we are going to continue this while loop because at the current time we have nothing. So let's increase the time and see who's going to join the queue later. But if the queue is not empty, then we're going to get the peak of the queue. That means whoever is in the top of the line or front of the line, and ask for the ID of that process. Then we are going to go, retrieve that process using processes bracket car. That's the index of that process. And we're going to reduce its remaining time by 1, because we're going to assume that at the current time, we're going to use that process as a current process that is being executed by the CPU. So its remaining time will be decreased by 1. We're going to increase the t. That's going to show the progress in our simulation. And then basically we check out the remaining time after the remaining time was reduced by 1. If the remaining time is 0, then the process is terminated. So it's not active anymore. And the turnaround time would be t minus the arrival time. We complete a new one, so completed should be ++, and then we're going to dequeue the ready. We're going to dequeue that process from the ready queue, and that's pretty much it. You can also print out some message saying, "Oh, I print this process got terminated with this arrival time, this turnaround time," but these are all just for your debugging purposes. I just put the printf and then I commented it out. You can check it out later, and that's pretty much all you have. You don't need anything else. This while loop continues as long as you have an incomplete process, and if all the processes are completed, we're going to get out of this function. Then you go back to the simulate.c, and then you're going to call the compute average turnaround time. This function, which you see here, is a static function. That means no one can see it other than the simulate.c functions. Basically, it calculates the total turnaround time, and then it's going to divide the total by n, and that would be the average turnaround time. I would suggest for large numbers, it might overflows, so replace int by long or something like that. And this way, you don't have to be worried about overflow, right? You may get a negative number if it overflows, but with the numbers I'm gonna test it in the current in this video, it's not gonna happen, so that's fine. Let's talk about what happens after you finish running your program with FCFS. Then you need to reset the processes again, because you need to try that same set of processes for shortest job first, and you need to use those same processes to simulate shortest remaining time and shortest and priority round robin, right? All of this should be tested with the same exact random numbers, but you need to reset the processes. I wish I use a better name for this. It's gonna be resetting only the remaining time, the active, and the turnaround time, because after one algorithm ends, like FCFS, you don't need to randomly generate the total CPU times or the arrival times or any other random numbers that we calculated before, like priority. All we need to do is reset the remaining time and set it equal to the total CPU time, because at the end of the first come first serve function, this has become 0. So you need to renew the value and set it equal to this total CPU time. At the end of simulate FCFS, actives are all false. You need to reset them this way, and the turnaround times are all big numbers, so you need to set them all to 0. And after you do that, then you can try again, right? So let me run this pretty quickly. I'm gonna head to my Ocelot terminal. I'm going to also show you Makefile. This is how my Makefile looks like. I have used -i-lm and -w as the flag. I have 2 header files and a bunch of O files that are going to be generated because of simulate.c, q.c. I have shown you FCFS, but these are not shown. These are empty. You'll see them later. But shortest job first, the C, shortest remaining time, the C, priority, the C would be like similar functions that will be similar files that you need to fill them out with functions to simulate shortest job first, shortest remaining time, and priority with round robin. And then the name of the executable is called PA2. Let me get out of this. After making, it said make is up to date, but let me show you a scenario when make is not up to date. If I say make, it's gonna compile everything for you and it's gonna generate PA2. Then I'm going to say, let's run PA2. It says it's not gonna work because you don't pass all of these parameters. Now let me pass it with some reasonable parameters. Let's say you have 100 processes which arrive at time 0 to 1,000, and then the mean of CPU time would be, let's say, 150, and the standard deviation would be 37, and then the round robin would be 187. The Q and round robin should be 187. And with that, I'm gonna hit the run button. It's going to print out this, right? That should be the output. The rest of it is nothing but the output that I wanted to print for stdout. So if you look at the way I have printed out the output for average turnaround time, you will see I have an fprintf with the ERR, and I have printf. So the reason I have these two is because this is going to print on the standard error. This is going to print on the output. I assume when you run it, let me clear this. I assume when you run this, you're going to basically redirect the standard output to a file like result.txt. And when you try to open result.txt, it shows you only the turnaround times of, or average turnaround times of the 4 processes. I only implemented this one, which is the first come, first serve. The rest of them is empty, so shortest job first, shortest remaining time, and priority queue would be empty. So it's going to show you 0. But you need to implement them so these 0 becomes non-zero values. One more thing I wanted to mention is that since the assignment wants you to draw a plot of d over a over d for multiple d's, and you need to run this simulation many, many times, not only once, we need to come up with an idea. We need to do this. We need to say, I'm going to run this main many, many times. So I'm going to call this main number 2, and I'm going to create another main, which I call it main. And then this time, I'm going to set n and k to the values that is specified in the assignment, which is, we have 4 scenarios. Scenario 1, n is 100, k is 1000. Scenario 2, 3, 4. This is a 2D array with 4 scenarios and 2 columns, 1 column for n, 1 column for k. And then I can create an array of arguments for my main 2 function. Say I have a dash n dash k dash d dash v dash q, and these are a bunch of mallocs which allocate 10 bytes. And then let's call that executable simulate. And then there's a null at the end. That's why you see 12 argument here. And then for different scenarios, I have 4 scenarios, but I only choose 2 of them, but you should basically go all the way to the scenario number 4. I have basically printed out the values of n and k on the standard error, so the user knows which n and which k we are using right now. And then in this for loop, I have moved or have changed the value of d from k over n all the way to 25 times k over n with the increment of k over n. And then the value of v and q will be a function of d and v. V would be d over 4, and q would be d plus v. You can define it this way. Let me just do this separately so you can see it easier. And then after all of that, we are going to print out all the parameters of our simulation on the standard error. And then we are going to print all the parameters of our simulation on the standard output. This is going to be a tab delimited table. So later I can move it to an Excel sheet, and I can print or can draw the plot of d over ATT over d, and then I have converted n, k, d, v, and q to different strings stored at different indices of argv. Index 2, 4, 6, 8, 10 would contain those values. And I have called the main2, which is my real main, with argc equal to 11 and argv equal to argv2. Now, I'm just going to run this program that I showed you earlier with a set of values for n, k, d, v, and q. This way, I can run this program hundreds and hundreds of times in a short period of time, but executing this master or the real main once, right? So what I'm going to do is I'm going to make all of these changes that I just showed you here in the Notepad++ in Ocelot. So let's go back to Ocelot. I'm just going to clear everything. I'm just going to say vim simulate.c. All the changes I want to make is one here. I'm going to get rid of 2 here. That's going to be my main. And then the original main becomes main.2, becomes main2. And then pretty much don't need to do anything else. Yeah, that's it. And also look at this. I only have the first 2 scenarios because if I want to run all the 4 scenarios here, it's going to become very long. But you need to convert this to 4. This should be 4. But for the sake of this example, I'm going to keep it equal to 2. And with this, I'm going to save it, compile using make, and then I'm going to say PA2. I don't need to pass parameters because my main has changed. All I need to do is press enter and see the output. As you can see, the output doesn't look good because I forgot to redirect the output to a file. Let's redirect the output to out.txt and press enter. Now it's going to only show me a standard error, and a standard output will be printed in the out.txt. As you see, I have only 2 scenarios, n equal to 500 and k equal to 10,000 would be the second scenario. Each scenario needs 25 different runs, so I'm waiting for the last run to be executed. After the last run is done, as you can see here, I only calculate the ATT for FCFS because I haven't done anything for the other 3 in this example. So after these are done, then you can vim the out.txt and see a you can see the tab delimited array, I'm sorry, table that shows n in the first column, k in the second column, v in the third column, I'm sorry, d in the third column, v in the fourth column, and then the average turnaround time for first come, first serve algorithm in the next column. And then the other ones are empty. That's basically for the other algorithms. Now let's get out of here. Next thing I want to show you is how to use Excel sheet to basically draw the plot of d over ATT over d. This is the plot that I created. If you look at the plot, it shows d over ATT versus d. These first few columns are going to be generated by my program, and then I calculated this column by dividing C2 by E2. So the C column, which is D, should be divided by E column, which is first come, first serve. And that's going to generate the D over ATT values. And then in this plot, I have drawn the scatter plot of d over ATT on the y-axis and d on the x-axis. And this is what I have seen. This is only for first come, first serve. You need to do another plot for shortest job first, shortest remaining time, and priority. And that would be one scenario when n is 100, k is 1,000. You need to do the same thing for the other value of an nk, the other scenario. In the other scenario, n is 500 and k is 10,000. And as you see, the plot has changed. So you need to draw 4 plots for the 4 scenarios. In each plot you have four different curves. One is for ATT, one is for first come first serve, one is for shortest job first, one is for shortest remaining time, and one is for priority queue. The last thing I want to mention is how to expand this simulation to other algorithms. So I just showed you the first come first serve. For the shortest job first, the code would be very similar to first come first serve. The only difference is instead of a regular queue, we use a heap or a priority queue. And the rest would be very similar. In the priority queue that you use, when you're trying to compare two processes, use their total CPU time for the shortest job first. The one with the lower CPU time has to be higher in the heap, or has to be, dequeued first, because of the nature of shortest job first. Because if the total CPU time is less, that means it is shorter, that means it should be executed first. The shortest remaining time would be similar to shortest job first. The difference is when you're using a heap or a priority queue to store the ready queue, you need to use remaining time as the key for every process. So we measure the priority of each process based on the remaining time. The last one, which is the priority with round robin, believe it or not, it's very similar to the first come first serve. Why? Because you're basically having 10 different queues. So you need to have an array of 10 of these queues, and it's going to be a regular first in first out queue. Because in each level you have to do a round robin, you need to check out or keep track of a timer. When the timer gets expired, you need to dequeue the process and then enqueue it back into the same queue. And then you should not look at low priority queues when we have a higher priority queue that is not empty. So you need to make sure that in your simulation, you don't look at all the ready queues. You need to only look at the ready queue with the highest priority. If that's empty, then you need to look at the second highest priority queue, and then move down to the lowest priority queues. And that's how you can manage your simulation for the last algorithm. That's pretty much it. Thank you for watching.